Lecture 28, Memory Profiling and Cache Grind. Okay, a kind of profiling other than the standard CPU profiling that we have done up to this point that is interesting to us is memory profiling. And that has to do with taking a look at where memory allocations are going and how many of them there are and sort of keeping a handle on what's happening there. It is, in particular, heap profiling that we want to talk about today. You will have done this kind of thing, perhaps, if you were looking at, why did my Java application run out of memory? Then you can look at it in the profiler, and it can tell you about, oh, hey, here's what I found. And you can spot the fact that, like, oh, well, this is a really big allocation happened, and it failed for some reason, or some objects are being retained, and it caused us to run out of memory. And you can definitely notice those kinds of things by using some sort of heap profiler or something to that effect. So, yeah, that's where we'll start with memory profiling. In particular, this gives us a look at the still reachable kind of stuff that's not been freed. We still have pointers to it, but it should have been, or we no longer need it, and we're keeping it around unnecessarily in a way that's just sort of making extra use of memory that we could be deallocating. During the rustification of the course, we dropped a bunch of Valgrind content. We didn't get rid of it entirely, but the Valgrind content is significantly shorter than it would have been under C and C++. If you recently watched that video, you will remember its memory error and leak detection toolset that we really needed in C++ and C code to be sure that we got it right. And Rust saves us from having a lot of those issues. However, when we think about what will happen in Rust with memory profiling, Rust's intrinsic features don't really save us anything on this account. It is always possible to allocate way more memory than you need or keep things around in collections forever in a way that wastes memory, and it doesn't violate any of the rules, so it doesn't help that Rust will trash anything that it thinks you don't need. As we'll see in an upcoming topic on queuing theory, that basically if allocations exceed freeze, then memory usage will tend towards infinity. Obviously, infinite memory is not available in your machine. Close, but not quite. But you will, at the very least, end up with paging, maybe an out of memory. In particular, I mentioned earlier a JVM kind of situation where you would get an out of memory error. It's not that the machine doesn't have memory, it's that your JVM is limited to whatever amount you defined in the beginning. And if you are exceeding that, well, you get the out of memory error, and it's a sign that something is wrong. So there's a couple things that we're going to look at as tools for memory profiling. The first one, DHAT, Dynamic Heap Analysis Tool. It tracks allocation points and sees what happens to them over a program's execution. An allocation point is somewhere in the program where memory gets allocated. In C, that would be malloc. In Rust, there are a few ways. The box new function or any other constructor might do it, and this information is all aggregated based on the program stack. So you get something like this that looks like one of the leaf nodes. This one's out of the documentation, and it is very information dense, so we'll have to break it down in, well, pieces. The program point that corresponds to this allocation is in the file tokentrees.rs at line 81. When we got here, the maximum number of bytes that were alive, that is to say allocated and still in a valid state somewhere, was 16,779,136. And that was, there were 65,543 blocks, that is to say that instances of memory that was allocated, all of which were about 256 bytes. That's the average. I mean, if we look at the code, we could see it will be 256 bytes allocated this many times, thus producing this amount of memory. The total allocation was executed here 262,171 times, and that gives you, some context as to how often it compares to other stuff in the program. We can see how long-lived any blocks are on average. A block allocated here lives for 4.91% of the program duration. If you had like a tiny figure there, it was like 0.004 and a large total of memory, it would suggest that actually this memory is excessively transient. You allocate it, you use it probably once, and then you destroy it. Doing something like having it in a pool would probably be more efficient to stop allocating and deallocating it. You can just overwrite the contents in your buffer whenever you need to, instead of create a new buffer, fill the buffer, throw the buffer away, seeing that the buffer would, in that case, live a very, very short lifetime. Seems like it would make sense. The reads and writes there towards the middle of the diagram tell you how often the allocated memory was actually used. In this case, 19% are actually read, and 33% are written to. That doesn't seem like very many, but if this is a vector that grows, for example, that might not actually be surprising. Because the vector resizes itself sort of dynamically based on usage. So as it gets full or close to full, it might double in size. And if that's the case, then at any given time, it's likely that somewhere between half and zero of the elements in this vector have been allocated, but they don't do anything. They're not in use yet. They're just excess capacity to make it quick to add a new item if a new one needs to be added. Okay. This doesn't look like a vector, though. It looks like trees, and the code would actually give away a little more detail about that. But it is data structure of some sort that we are looking at. We can get some extra information if all the blocks allocated are at the same size, telling you how many times each byte in the blocks was accessed. So that could also be fairly interesting for looking at something like allocating an array. Do we need everything that's in there? Nice to think about. And then there are parents. So going up the tree, then we can also look to the allocation points that share a call stack prefix. If there is a little circumflex, it's like that hat thing, before a number, it indicates that line is copied from the parent. If there is a number sign or pound symbol, it indicates that this line is unique to this node, so it's interesting and relevant here only. And if there were a sibling call, it would diverge on line 10, not calling, say, parse token trees until closed limb, and so on and so on. And at the parent level, you also get an insight into here's what happens with all of the children nodes as well. So every function, every interesting point. Originally, I intended at this point to show actually looking at a program using the dynamic heap analysis tool. Unfortunately, on the ECE servers, the version of Valgrind that we have is not up to date enough. It is not 3.15, it is in fact 3.13, which is close but no cigar. So we'll, as a limited substitute for that, take a look at a screenshot here that's in this blog post about it that gives you some idea of what it looks like in context when we get some output for some data. It is a little bit small. Unfortunately, the quality of the image is not great, so it might be a little bit hard to read, but nevertheless, it gives you some idea. Right, there is a little graphical browser where you can take a look and see, okay, we start up here at the top, and it has 25 children, and this child here, highlighted in yellow, has certain information associated with it about memory being allocated, and so on and so on, and you can follow the tree down as is necessary to dig into areas that are interesting to you and discover anything that stands out as unusual or strange. Again, keeping in mind that you're looking for things like memory that's living a very short lifetime, memory that's allocated but is never read or written, memory that leads an exceedingly long lifetime for no apparent purpose, so just keeping it around forever would be a big deal. Anything where we're allocating way too much memory for reasons that are not obvious, that we don't have a good explanation for. The memory profiler we're actually going to use is called Massif. This is obviously a joke on Massif, combined with the name Sif, a Norse goddess associated with the Earth, and at least in the Marvel movies, shield maiden to Thor. You may find that the version you're more familiar with. While we're on the subject, Sif is really not happy with Loki because at some point he cut off her golden hair, and at least in the Marvel films, it came in dark. That Loki, what a trickster. I mean, by the end of this, you will probably believe that this course is ECE 459 Norse mythology, but it's not. It's about programming. Okay, what does Massif do? It tells you some information about how much heap memory your program is using and also how the situation got to be this way. And the docs include this little sample program which allocates some memory. And it's non-idiomatic Rust, really. Professor Lamb has translated it from its original form to Rust. But here you go. We have a function main, it creates a vector, and it pushes some stuff into the vector, calls f, calls g. F does some stuff, allocates a vector, forgets it, calls g. G allocates some memory, forgets it as well, that sort of thing. Great, sure. It gives you some idea of what's going on. And like with Valgrind, after you compile, you run it with your Valgrind command specifying tool equals Massif, and then it gives you some output. But that's all the output that it gives you. Well, that doesn't look very useful. What happened? Your program executed slowly because it's Valgrind and it's running it under the supervision of the tool, and that really slows it down. Okay, that's fine. But we didn't get any summary on the console the way we do with memcheck or Valgrind or the other thing we're going to talk about later, cachegrind. Instead, a massif.out.pid file is generated with whatever process ID it was of the process that we were just observing. Okay, we can open that up in our text editor, but it's not especially human readable. It's not as incomprehensible like some of the other versions, but actually what we need is to use a tool msprint. And this msprint tool gives a better human readable view of what actually happened. If you look at the output there, which I suggest you pipe to less or something, otherwise a ton of data gets thrown at the console and that might not be the most legible. It looks more user-friendly, and although it's called msprint, it really has nothing whatsoever to do with Microsoft, I promise. And our post-process output looks something like this. Okay, let's actually take the program for a spin and see what's going on. Okay, we're ready to actually take it for a run, and this was over with quickly, as we would expect, and it produced this massif.out file, as I said, which, well, you can read it, but it's not that useful. It's really hard to make anything of it. So let's get on with it and look at msprint of this file. We'll pipe it to less. Okay, as I said, the bar graph that we got isn't super helpful, because it looks like for a long time nothing happens, and then all of a sudden, kaboom. Well, what happens is we gave this a trivial program where a lot of CPU time was spent doing setup and everything, and our program ran for a tiny fraction of time, and we didn't actually observe very much that was useful because it ran for a fraction of a second. So what I'd actually like to do is run this again, except instead of having the time unit be, well, time, the time unit is bytes allocated, which sounds silly. Bytes are not a time unit. It's, like measuring, oh, this deer is 47 hamburgers tall. Anything to avoid the metric system. No, but realistically, the goal is to make your x-axis bytes as opposed to time units, and that would be a better name for it, but this is what we're stuck with now. Okay, and now we can look at our output from this. Our new PID is 9957, and that actually looks a little bit better. That's more something that we can do something with. Okay, We can see from the text below the graph there that there were 48 snapshots taken. Most snapshots are normal. They're used just with the colon characters. Detailed snapshots are done with the @ symbol, and then the peak snapshot uses the number sign. So by default, every 10th snapshot is detailed, and the peak snapshot is, well, where was memory consumption at its greatest? Okay, that's interesting. If we scroll down a bit and look at the details, we'll see that the brief snapshots, the normal ones, they just tell you, okay, at time n, snapshot n is 1, 568 bytes have been allocated, and that's the total, and the useful heap was 552, and the extra heap was 16. That is, what's that about? Well, the extra heap usually happens for allocating, say, the overhead stuff related to keeping track of allocated memory, or if you ask for some strange number of bytes, it might get rounded up to make it a little easier for the memory allocator to just allocate you that and waste a little space in what you might have covered in an operating system course as internal fragmentation. Okay, and then a detailed snapshot tells you where specifically memory was allocated, and it gives you a nice breakdown of everything. So 98.27 was done using heap allocation functions, and we can see 55.41% happened in main at this line, and dig down into some of the stuff that is the libraries, but ultimately we can see in our code where it happened, and then 29.87% happened in main here, and 12.99% also happened there. Okay, so we're just getting set up, and as we go on, we can take a look at the peak snapshot. We can look at other snapshots, and we will start to see that more information is becoming available to us about where has the memory gone, where is it going, and this is somewhat helpful in tracking down what caused a memory allocation. It tells you, some lines about, okay, here it happened, in main, it here or there, or this function or that function. Anything that tells you where it came from. As before, it doesn't really tell you anything. It doesn't really tell you anything about where memory should be deallocated, if it should be deallocated, but if you're curious as to why am I running out of memory, or why is memory consumption so high, knowing where it gets allocated can really give you a lot of information used to track it down. We should also keep in mind that when it comes to, say, the time index, the heap, the max one isn't necessarily totally accurate, because, well, the peak is recorded really actually only when there's a deallocation. Because if you're climbing, you don't declare yourself to have reached the top until you've finished climbing, so to speak. Otherwise, the tool would constantly be overwriting the same place over and over again, saying, this is the peak, no, this is the peak, no, this is the peak, which just kind of wastes time. It would be easier to just wait until there is a little step down, and then you go. And there's also a little bit loss of accuracy that's relating to speeding things up. That's to some degree expected. The information won't be exactly perfect, but it will be close, and that will give you a little bit of guidance as to where is my memory going, and hopefully you will identify a problem if you're having one. Okay, so yeah, Massif has found the allocations in this program and sort of broken it down to a tree structure that says here's how it all looks and here's how it works. In particular, in this example, if we look over here at this line here where memory is allocated in function G, we can see that. We can also see that it was allocated in function F, and some of it is one calls the other kind of thing. Some of it's allocated in main directly. Some is allocated in F as called from main. It gives you all the paths that break down where is the memory being allocated from and where is it going. So that's good. We used to say, incidentally, it's probably a good idea to run Valgrind first and make it happy. Make sure there aren't memory leaks, because you would just be complicating your life by having memory leaks and you're trying to track where the allocations are going. But that's not really necessary anymore. Again, still could happen, but you would have to be doing something complicated or difficult, and you're probably not. It's probably okay. The way that your program is, if it's entirely Rust, and you don't have to worry that you're leaking memory, and that would therefore not be a problem. Still, Massif can tell you some interesting stuff about your program and help you find a problem, such as so memory usage climbing over a long period of time. It might be slowly, but if it's never decreasing, that suggests that your memory is filling with junk somehow. You are remembering things for some reason, and it can be fine to remember some information. It might be very helpful in terms of keeping track of recently used items. But if you are never taking anything out of that collection, you are possibly just wasting a lot of space because you are just filling up memory with junk that you never need again. Another thing you could watch out for are very large spikes in the graph. If there is a significant allocation and it's, again, used very briefly and then deallocated basically immediately thereafter, that would also prompt some questions about why this is the case. And maybe it would be better if you have some alternative approach where you don't have to do quite as much allocation or deallocation. Other things you could do with Massif, we could look at stacks. If you choose, you can set stacks equals yes. If you're worried about running out of stack space and you're trying to figure out what's going on with that can tell you. I'm usually hard-pressed to come up with a good example of where you would want to have that detailed of a look into the stack, but you could if there's a reason. The option is there for you. You can also use Massif to look into the children of a given process. You can look at anything that's split off with fork or its equivalent. When it comes down to it, and you can also look into low-level stuff. If you have a very low-level program and it does stuff with like mmap as a system call, you could in fact ask Massif to look at that for you, and it will tell you about where is your memory going and why did this happen and how often does this happen, and all that kind of stuff which you otherwise might not see. And it can do profiling at the page level as well, so even asking the operating system, so however the memory gets to be there, tell me about it, and the operating system will gladly provide that kind of information as it needs. So yeah, as is often the case, we've looked at it with a trivial program. Maybe we could also look at it on a program that is less trivial. Okay, let's take a look. This is going to be the producer-consumer problem with the optimized version. That is the one where we release the mutex sooner rather than later. Takes a little bit to run, as we will see. Okay, and we're done. Let's look at the output file. Okay, interesting. So over time, we see that memory gets allocated pretty regularly until it sort of all comes to an end right before the end of the program. All right, let's find out why that happens. See if we can spot it in the peak snapshot. Okay, let's take a look at this one. Okay, so it looks like a fair amount of the memory that's allocated goes in a vector. that makes a certain amount of sense, I would think, because we're putting stuff into the vector, and we are taking stuff out of the vector as well. A little tiny bit of memory goes into printing at the time of the snapshot. A couple other things related to, say, the thread having its own memory. But yeah, it looks like pretty much all of the memory has gone to our vector, and it's the kind of vector that will grow as is necessary. Interesting. Okay, let's try a different program. You know the one. Actually, yeah, we'll do the parallel one because we don't want to wait forever. Let's give it a go. Right, through the magic of editing, you didn't have to wait through that. And we could see that in this program, really the memory that gets allocated is pretty constant. That's to our expectation. There isn't a whole lot of allocation and deallocation of stuff here. We allocate our data, we operate over it, and then that's it. We're off to the races, and we don't really need it again. We don't have to allocate more. We don't have to get rid of it. There is a little bit of stuff where some rayon material gets allocated, but otherwise not too different from expectation. Let's try one more. Let's see what it makes of the Cuda program. Well, that was certainly over with quickly. And as we can see, it actually took a little bit of time to compile all the results. But let's see. Okay, so peak in memory allocation actually took place at the beginning, and a lot of it appears to be CUDA-related stuff. As we can see, 43.96% has to do with allocations that take place in the Cuda library when we invoke the init function for Rust to Cuda. So that's interesting. Unexpected, if you will. As we can see, the rest is more to our expectation. We only have a bunch of init stuff, and the rest will be, when we actually allocate some vectors and things, we'll see that's where time is going. So we'll skip to the end here. We have a fair number of snapshots. Yeah, the other thing that I didn't mention previously is that, like, if it's a small amount of memory here, it's 28,000 bytes or whatever, it's less than 1% of memory, it won't report it individually just to avoid spamming you with a huge amount of data about a tiny allocation here. But just keep that in mind, that if you're looking to track down something small, you have to adjust the threshold to make more sense. Okay, yeah, as we can imagine, stuff is pretty verbose, but here, interestingly, in this snapshot, we can see that 19.68% of the data here is allocated in Cuda when we do create and push, so we're creating our context. We will see also here that 28.77% was done by our by an earlier create and push. It is definitely interesting. It shows you just how much overhead there is and all the Cuda libraries and everything that are necessary to actually launch your program, and not that much of it has to do with initializing anything. If we look in initialize accelerations, for example, here this vector here is 15% of the memory allocation in a snapshot, where initialize accelerations is 15%, and initialize positions is 19%, and they combine for 34.75%. So they're big, but the remainder is all going to all the Cuda stuff, which turns out to be quite a lot, because 35% being these are the vectors that we allocated. Doesn't, I don't know, surprises me anyway. It doesn't quite match what I would have expected. And we can see that 8% here in Cuda, and then another 8% in Cuda, and then there's a whole bunch of tiny stuff that combined in 226 places. So that's the detritus, that's the leftovers that we're not that interested in. Here another 5% allocated by Cuda, by creating the context and pushing, and here again create and push. And so on and so on. So each individual Cuda item isn't that big. When you combine them, 8 plus 8 plus 5 plus 3 and so on, it really does add up to where the memory that we've specifically asked for in our vectors turns out to be pretty small, being only 1/3 of the actual allocated memory, the rest being all these Cuda fragments. Neat. Tells you something that you didn't necessarily know. And if you were worried about the Cuda program running out of memory, then you would know, looking at this, that actually you don't have to sweat it quite so much how much memory your vectors are taking up, because they're not the biggest part of the problem now, are they? They might be the only thing that you can shrink, which might be a reason why it would be a reason to address it, but otherwise we know it's not where the majority is going.